In this video, I'll give a quick overview of stats, and this is especially useful for those who are unfamiliar or have limited knowledge of statistics, because it's very hard to compress a whole subject into a short video. So when we collect quantitative data, which is mainly what we're dealing with when we talk about stats, there are several measures that we can use to make sense of this. Measures of central tendency are one of these, and they help us as a way of summarizing an entire distribution with a single score, which means can we make sense of the data that we have distributed across the population with one score. And there's three main scores that we can use. The mode, which is the most frequent value, as in the value that's most frequent within your sample. This is probably the least precise of the measures of central tendencies. The second one is the median, which is the middle value. So literally the number that, once they're ordered, falls in the middle. But one of the limitations of calculating the median is that this may not be representative of the data set. And then finally we have the mean, which is the average. So it's calculated by the sum of all your variables divided by the number of total variables. The mean can be misleading if, for example, the dataset contains particularly atypical low or high values. There's also, when measuring the central tendency, one of the things that happens is that we lose a lot of important information. So it's also important to describe the variability of the data. So the measures of dispersion, not just what is the average or the mean or the mode, but kind of how different is the rest of the data set from that. So we can talk about range, which calculates the difference between the highest and the lowest score in the data set. And this is probably the simplest measure that we can have here. We can have the variance, which measures how far each observation is from the mean. Or we can have the standard deviation, which is probably, again, the most important measure here. And it shows the dispersion of the data around the mean. So how far your data is from the mean. And in general, this means that the larger the standard deviation, the more the data is dispersed around the mean, or spread out, let's say. So we've talked about distribution of the data, particularly in relationship to a mean. And often when we talk about distribution, we refer to normal distribution, which is, it's a probability function that describes how the values of a variable are distributed. And in nature, in our real world, there's lots of things that follow this normal distribution, such as the height of people, blood pressure, or even marks on a test or exam. And when we have a normal distribution, the mean, the median, and the mode are all identical. They all fall in this middle bell curve that you see here. So this is the bell curve, this is your mean, median, and mode. And this curve is symmetrical. So 50% of the values are less than the mean, and 50% of your values are greater than the mean. In relation to variability, if we look at it in a normal distribution, the variability basically tells us how flat the curve is or how pronounced the peak might be. So a low variability means that there is a very tall spike in the distribution, because a lot of the data is very similar to one another. In a medium variability, this is the blue line in the middle, it's more spread out, and in a high variability, it means that the data points are very different from one another and very dispersed from the mean. And that's what you want to do. You might have heard a lot about in the news in these days about flattening the curve. This is basically what we are trying to do in the current pandemic situation, for example. And then with standard deviation, again, we talked about how it shows the dispersion around the mean. So the larger the standard deviation, the more dispersed the data is. And within a normal distribution, you can calculate the standard deviation as the square root of the variance. And you'll find that that will give you the value of 1 standard deviation. So this kind of arbitrary distance that will depend on the data set that you have, because it will depend on the variance that you have. Oops, sorry. And within 1 standard deviation from the mean, you get 68% of your sample. Within 2 standard deviations, you get 95%, and within 3 standard deviations, you get almost 100% of the values. So let's try to translate into a more practical or concrete example. So we have a data set here. This compares 2 independent groups, people that eat kimchi and people who do not eat kimchi. So kimchi eaters and kimchi abstainers. And we want to know which group is faster in a race. So these are our different data points, and we can calculate the mean, which tells us that kimchi eaters are essentially faster than kimchi abstainers. Now, we might, because this is a small sample, we might just quickly glance at the data and kind of say, well, yeah, we could have kind of guessed that kimchi eaters are faster than kimchi abstainers. However, we need to be careful when measuring, when looking at our sample, because we need to think about whether it's representative and we have included enough data points. Because say, for example, you had just 1 extra data point, this might completely screw over your assumptions about the data point, the results. So say we had added an extra data point here where a kimchi eater is a lot slower and a kimchi abstainer is a lot faster. We suddenly have very 2 similar means between the groups. Still different, kimchi eaters are still faster, but are they significantly faster from kimchi abstainers? Well, the standard deviation might help kind of give us a bit more insight. So we can see that in the kimchi eaters, the standard deviation is 0.9 seconds. So it means that the distribution around the media is a lot more condensed. Whereas kimchi abstainers is more spread out. And this is just to kind of show that obviously we have a small sample set here. We would be doing this on a much larger sample or data set. And we need to think about how do we understand the difference between 2 different means. So let's assume this is the data that we have, but like blown up to a lot more data points. And we look at their normal distribution. And we see that kimchi eaters, they both have a normal distribution. And these 2 bell curves are somewhat overlapped. But we don't know if this overlap suggests that the difference between these 2 means is significantly different from one another or not. So there is no way of actually being completely sure that kimchi eaters are faster. What we can do, thanks to inferential statistics, is that we can have an indication of how sure we are that there is a difference. And one way of doing it in this case is using what is called a student's t-test, which is an inferential statistics used to determine if there is a significant difference between the means of two groups. And we use it in this case because we have two independent groups, kimchi eaters. If you're a kimchi eater, you cannot be a kimchi abstainer, and vice versa. And what the t-test does is, like I said, it looks at the means and the variations between the two groups and compares them. And in comparing them, it produces a t-statistic or a t-value, which will then map onto a t-distribution. And this t-distribution tells us what is the probability of getting this particular value. So just to keep it kind of very abstract, what the t-test does is basically it compares each score of our data set against the mean for its group. So each score from kimchi eaters against the mean of kimchi eaters, and each score of kimchi abstainers against the mean of kimchi abstainers, and then produces this t-statistics. So in our case, that value is going to be 4.08. Now, if we look at the t-distribution, what we see is that 4.08 falls down here. So this distribution suggests that if the two bell curves that we saw earlier, these two, were overlapped and there was no significant difference, they would fall here in the middle with the zero or null hypothesis. But actually the t-value suggests that we are more close to this tail end of the curve. And this basically tells us that 4.08 is not very likely. So the difference between the means of kimchi eaters and kimchi abstainers is essentially 4.08, roughly. And it basically tells us, because it's down here, it's not very likely that the difference is given by chance. It's not a random, it's not by chance that it's a difference, but actually that there is a significant difference between the two groups. So this can then be used in our what is called a null hypothesis significant testing approach to make a decision about our hypothesis. So whether we think that the two groups are significantly different or not. And a null hypothesis, in this case, is what we're looking at, is a general statement or position where there is no relationship between two measured phenomena. There's no association. So what we're trying to do here is to reject the null hypothesis in order to say, actually, there is a difference. There is a relationship between these two measured phenomena. So when we get our t-statistic, we get 4.08. We also get a p-value, which in our case is 0.0008, 0008, sorry. And this p-value is basically our significant value. It's our indication of how sure we can be of that difference. And in many fields, a p-value is considered significant if it's below 0.05. So in our case, it is below 0.05, and it can be considered significant, which means that we can reject the null hypothesis. We can say, yes, there is a relationship between the two measured phenomena, and kimchi eaters are indeed faster than kimchi abstainers. One of the criticisms, though, that we need to be careful with null hypothesis significant testing is that it's quite a controversial way of testing currently, and there are some disciplines that have actually indeed banned it because it can encourage like fishing expeditions, and yes, it is a critical piece of information and it can help us determine an indication of whether there is a difference or not, but it's inadequate as a sole tool for statistical analysis. So successfully rejecting a null hypothesis might actually offer no support for research hypothesis. So we need to be careful, which means we need to think about what is it that we are looking to test. And when we set out our method and our research question, we also need to think about how we're going to analyze that data. And there are different tests that can be done with quantitative data, not just the t-test, but all sorts of others. And this will depend on a number of different factors. It could be based on whether you are looking within subjects. So that means if the same participants are repeating a test, for example, over time, if you're doing a before and after comparison, or if you're doing a between subjects, which means different groups of participants will get different treatments or interventions. And this is the case, for example, when trialing a new vaccine, some people might get a placebo, some people might actually get the vaccine. And that's a between subjects design. You can also think about the number of factors that you're looking at. Is it just whether they are kimchi eaters or not? Or is gender also another factor that you want to look at? Is age another factor? Degree level, for example. And again, within that, what are the different levels? If you're looking at degree, is it undergraduate, postgraduate, doctoral level, for example, and so on. So depending on the data that you end up collecting and how it's distributed, you will have different types of tests. And there's all sorts of resources that you can look online to figure out what is the most appropriate test for your data. But one thing you really need to keep in mind is that there are different types of data. They can be grouped into two very broad categories or groups. One is categorical data. So this can be divided into nominal and ordinal data. So nominal data is data that is not ordered and that is organized in categories that are mutually exclusive. So whether you are male or female, there's no order in whether one comes first or the other, and they are mutually exclusive. Ordinal data is categories that again are mutually exclusive, but this time they are ordered. So first place, second place, third place, for example. Numerical data instead can be divided into interval and ratio. So an interval data set suggests that that the data can be ordered, and you can identify differences between the data points, but there is no inherent starting point. So that is, for example, temperature when we measure it in Celsius. A ratio is kind of an extension of interval data, in that it's ordered and you can still measure differences between the data points, but there is an inherent zero. So this is, for example, height. So if we measure height in centimeters, there is a zero. You're either not tall at all and basically don't exist, or you kind of grow bigger and bigger and taller. So based on the data that you have, you need to pick the appropriate tests. And it's really important to figure out which is the most appropriate test, because this can lead to either very meaningless results, but it can also increase the chance of either type 1 or type 2 errors. Type 1 error is what is usually called a false positive, whereby you reject a null hypothesis that is actually true. So you say there is no difference between these two groups, but actually there is. So I think this picture kind of nicely depicts it. Type 1 error is when you're telling a man, yes, you are pregnant. Type 2 error is instead a false negative, where there is a non-rejection of a false null hypothesis. So in this case is you would be telling a heavily pregnant woman who's like maybe 8 or 9 months pregnant, actually, no, you are not pregnant. Have a look online at the different tests that there are. There's resources also in the textbook for the module on different tests that are available, but they kind of all follow the same principle of the t-test, and that's why I've presented that one today.